and I'm the Director of Professional Development at the Wildlife Conservation Society, and I'm going to be moderating today's presentation. During the first half of our presentation, Jason Aloisio will present background information about urban ecology and present some of his ecology research. And for the second half of the presentation, Paloma Krakower will explore teaching applications for the science concepts presented. Before we get started, let's quickly become familiar with some of the tools available in our virtual classroom. First, we'll start with the Talk tool, which is at the top of your panel outside of our slides. I will enable this during our question and answer portions, and you can present your question via your microphone. If you don't have a microphone installed, feel free to type in the chat box lower down on this panel your question, and we will respond to everyone via our microphones. We also have some other interactive options that I'm going to run through right now. In our participant panel, you'll see 4 boxes. First to the left is a smiley face. Go ahead and click on that smiley face so I know we are all there. Awesome. The next tool we'll be using from up there is the hand tool. That hand lets us know that you guys have a question and can allow you to have the microphone privileges so you can ask your question to the presenter. Go ahead and click that hand tool now so I know that you know where that is. Awesome. And finally on that panel is a polling option. At certain points in our presentation, we will have a poll for you guys to respond to. Right now it's a yes or no poll. There's also a multiple choice option. So when we ask you to respond to a poll, that is the point where you will click on your response in that option. The next interactive option is our whiteboard. So right now you'll see a map of the United States, and right now we're going to use the laser pointer to allow you to tell us where you're joining us from. So on your panel, you should see a nice star icon. This is your laser pointer, and go ahead and click that icon and then click on the map where you're joining us from. Fantastic. If your location is not on the map, you can go ahead and type it into the chat box. I'm going to encourage you to type and use that chat box throughout the presentation to get out your questions. We'll log them, so when it gets to the Q&A time, we'll make sure that they get answered in the order that they were asked. So without further ado, let's get started. I'm happy to introduce Jason Aloisio. He's an urban ecologist, a PhD candidate, and the program coordinator for Project TRUE, Teens Researching Urban Ecology at the Wildlife Conservation Society. So using our applaud tool that's underneath your smiley face, let's welcome Jason.
Hello everybody, how's it going? Can everybody hear me? All right, thanks Paloma. Amanda hears me. Can I get some pluses or a thumbs up from everybody else? Can you guys hear me, Diane, Angela, and Summer?
Jason, it looks like they've got the check mark saying yes, they can.
Oh, okay, there it is. Okay, well, it's wonderful to have you guys here today. And I am a PhD candidate at the Fordham University and the program coordinator for Project TRUE, which stands for Teens Researching Urban Ecology. and I'm going to talk to you today a little bit about discovering the ecology in the urban jungle, and touch on some of the research that I'm doing on green roofs. And specifically, I'm going to really look at plants and plant usage on green roofs because I'm really a plant ecologist. And I'm going to start off with a little bit of what may be review or maybe some concepts that you've heard before. But I just want to go through them to make sure we're all on the same page. And then I'll go forward into my research, and that can get a little heavy. There may be some figures in there, but I'm going to take some time and go through them. And if at any point in time you would like to ask a question, or if you would like to stop me for clarification, please write something in the chat box or raise your hand or whatever. Okay, so let's get going, and let's first talk about bees. In China, over the last several years, the pollinators have been in such decline. There are certain areas of China that no longer have pollinators around. And people now have to climb up on trees with little paintbrushes and take pollen from one flower and add it to the next flower. And as we all know, pollination is critical for fruit production. And about 75% of all crops require pollination by bees or other species in order for them to develop from flowers into fruits. And I love this picture right here because it shows these guys climbing around, and the only way that this picture would be any better if it was like John Belushi in a little bee outfit kind of climbing up there. But alas, he's no longer with us. But this, I think, shows how important the services that are provided by ecosystems are to humans. Without bees, without nature, we would not be able to get fruiting plants and get fruit. And so we can actually value ecosystem services, and there's a whole different there's a whole variety of different ecosystem services. And right in the middle, we see ecosystem services are what nature provides to us for free. Now it's free right now because all we have to do is just leave it, let it be, and nature will automatically clean our air, and it'll provide fish in the sea for us, and it'll provide clean air for us. However, as we change the planet, we change the dynamics and the kinds of ecosystem services that we're able to get from the natural environment. And so ecosystems, as we all know, are not static. They're constantly changing. And they change, this is commonly referred to as disturbance in the ecological literature. And ecosystems change over time through various kinds of disturbances. One way that an ecosystem might change over time and subsequently affect the ecosystem services that are provided by that natural ecosystem are through this guy right here. Can anybody tell me what's going on right here with this tree? I see Summers writing, possibly. What do we got going on there? Diane? We're all taking a stab at it, maybe? When we look at that tree, what's happening to that tree right now? Anybody have a guess? What organism might be affecting that tree in some way? Is that a hand raised?
Yes, it is. Diane, you should be able to speak.
sorry, is this coming from beavers?
Yes, it's coming from beavers. So here's our beaver right here. And our beaver is what some ecologists might call an ecosystem engineer. It changes the ecosystem. It engineers the ecosystem. And in particular, it creates a beaver dam, which turns a terrestrial ecosystem into an aquatic ecosystem. And it could change the dynamics of an entire watershed, as a matter of fact. And it creates new food webs and changes the kinds of ecosystem services that might be taken from the environment before the beaver builds its dam. So I like to think of the beaver sort of as an analogous organism to us humans, because humans have vastly changed our environment over time. The top of this slide shows what Manhattan looked like 400 years ago. And it shows lots of trees, and it shows wetlands, and it shows the coastline. And over the course of about 400 years, we have vastly changed what this island now looks like. And in fact, we've changed the shoreline very dramatically when you look along this bottom area where Battery Park City is. And so this process of change, let's see slides here. This process of change is people affecting nature, people engineering nature. But of course, nature still affects people in a variety of different ways through these ecosystem services. Of course, nature can also provide ecosystem disservices like natural disasters, which we'll touch on in another moment. So some ecologists have described, and some geologists have described, the current age that we are in as the Anthropocene, or the age of man. And in a recent study published by Ellis in 2010, he determined that greater than 75% of ice-free landmass is altered by humans in some capacity. And that would include rangeland, urban land, agricultural land, suburban development, all kinds of different things. And I really like this picture because it sort of illustrates the extent of which we are now a global interconnected community that has been changed very dramatically by humans, ecosystem engineering humans. We have a great deal of connectivity between areas, such that species distributions have vastly changed. For example, apple trees, those trees that we were having to pollinate by hand in China, apple trees are all from a single forest in Kazakhstan, and were spread across the entirety of the globe. In addition to that, we fragment our habitat by putting down roads, and we introduce all kinds of new pollutants and chemicals into the air and soils, greatly changing ecosystem dynamics and the ecosystem services that are provided by those ecosystems. Okay. Now, I don't think it's all doom and gloom, and I, as a matter of fact, think that our new technology that we have developed over the years has provided lots of great things for us. I now have the ability to get into a plane or get into a car and travel far away and see this beautiful planet. And I'm also the product of medical know-how, seeing that I would probably be a crippled right now if I didn't have a great surgeon to put my knee back together after I broke it skiing, or other diseases that people get inflicted with and that we now have cures for. So the technological age has many good things to it. However, we are also inflicted by higher frequencies of natural disasters in recent years. And this image right here is pretty iconic for anybody from the Northeast. We were inflicted by Storm Sandy several years ago, and that is a subway station filled with water. So that's not supposed to be. That is a bad thing to be occurring. And we also see that infrastructure we built, engineering feats that we have done, such as this bridge right here, have been just wiped clean by nature. And so it's important for us to understand these features and understand the relationship between humans and nature so that we can better manage our growth as a human population and manage that relationship with nature. And so urbanization is, or the growth of the human population, as we know, is increasing drastically. And specifically, that growth is occurring in highly urbanized areas. And an urban area can be described as a high population dense area with a lot of paved surfaces. And these are things like roads, buildings, sidewalks, and parking lots. And as we pave over natural ecosystems and natural surfaces, we actually lose a lot of those ecosystem services that were once provided. And we actually have environmental degradation, so we lose those ecosystem services, and we actually also see higher incidences of negative human health implications, like higher degrees of asthma or obesity in urban areas, and especially in poor urban areas. All right. So we had a natural system at one point in time, and it was lush and filled with lots of different species. It was rich in biodiversity and rich in ecosystem services. However, over time, we pave that city over, or we pave that space over. We lose those ecosystem services. But this isn't the end of the story. We can actually mitigate the loss of these ecosystem services or reintroduce elements into the urban matrix that will increase our ecosystem services once again. And how do we do that? Green infrastructure. Who's familiar with green infrastructure? Can I get maybe check marks or a show of hands? Who's heard green infrastructure before? Okay, Angela, great. Summer, no, okay. Diane? Not sure. Okay, well, we'll go on. Green infrastructure really refers to areas with vegetation that are managed inside of cities. So green infrastructure can be things like parks, and things like street trees, and things like urban gardens, and things like green roofs or rooftop gardens, which I'm going to talk a little bit more about in a little bit. But first, I want to talk about what might happen here on the ground level. If we introduce green infrastructure, oops, jump slides. So as humans, we are these ecosystem engineers, and we've created this urban habitat, and we can design this urban habitat to increase the amount of ecosystem services that we do in fact have. And one way here are these beautiful green roofs. Okay, let's see. Oh, here's the slide. So this here is a ROWB, right-of-way bioswale. So a right-of-way bioswale is basically like a street tree, but a street shrub. Instead of putting a street tree on the road, what they do is they cut out a piece of the sidewalk and put a little planting bed with some plants. And when water is running on our paved surfaces like our roadways and our buildings, when it's running along, it wants to find the path of least resistance to go down into our sewers. But having water go directly into our sewers can be problematic for some reasons that Paloma will talk about later. And instead of having it go into our sewer and cause problems for our surrounding water and aquatic and marine ecosystems, we want to try to stop that water right where it sits and prevent it from going in the sewer. And so we basically put these sponges on the roadway to absorb that water, and they are called bioswales. And they're just little planting beds that are cut in the sides of the roadways. And so New York City has been doing a series of pilot studies to understand how effective are these little sidewalk gardens, these bioswales, at reducing the amount of water that runs into our sewers. So this image right here shows sort of a picture of a mini urban watershed where water from this surrounding area is going to flow in the direction of these arrows when the rainwater and precipitation comes down, right? When precipitation comes down, paved surfaces can't absorb it, so the water hits the surface and runs off. And we have sewer pipes, catch basins where these little blue dots are. And what we want to do is try to stop the water from getting into those catch basins and causing problems for aquatic and marine habitats. And so we put these bioswales all along the roadway. And in fact, over the course of a period of study, the city found out that when you add green infrastructure, GI, green infrastructure, these bioswales, you actually see a 10% decrease in the amount of volumetric runoff. So that's just a measure of the amount of water that goes from our paved surfaces into our catch basins. And so we can see that there was about a 10% decrease here in storms that were less than 1 inch. And then in storms that were greater than 1 inch, we saw a really big decrease, almost 20%. So that's great. More plants in the city, and we're reducing the amount of polluted water that goes into our surrounding waterways. So that's great. Green infrastructure seems to be doing some pretty good stuff for us. And this, a green roof, is another example of a piece of green infrastructure. In New York City, about 35% of the total surface area of New York City is in the form of rooftops. These rooftops act like bathtubs that collect water and then just put them directly into our sewers, causing that pollution. Instead, we can put green roofs or rooftop gardens on them to act as sponges to absorb that water. But not only will a green roof absorb stormwater, reducing pollution in our surrounding waterways, but it'll also do a bunch of other things. It's a functioning ecosystem and providing ecosystem services. So the plants that are on that roof are actually going to improve air quality. They're going to capture CO2, and they're going to capture particulate matter, and they're going to pump out O2. Not only that, but they're actually going to keep the roof cooler. And so they're going to reduce something called the urban heat island effect. And they're going to reduce temperatures inside of that building. By doing so, we're using less air conditioning and less electricity, and therefore using less of a carbon footprint to keep our buildings cool. So green roofs provide a lot of great benefits. Oh, and of course they may increase the biodiversity in the city by creating more habitat space. And as you can see down here, this is just a small number of the many studies that have demonstrated all of these services and quantified these ecosystem services that are provided by green roofs. Now, green roofs, you might ask, well, what kinds of plants are we growing up there? These are the most typical kinds of plants that we grow on a green roof. Does anybody have any idea what these plants are called? If you do, you can type it into the text box. I'll give it about 10 more seconds if anybody has a thought. All right. These plants are sedum. They are succulent species, and we call them succulent species because they're sort of similar to cacti. And these species have really waxy surfaces on them and big, thick leaves that allow them to hold on to the water that they acquire for long periods of time and not lose it through evapotranspiration through stomata. And these plants are typically found in environments where there's rocky soil with very little water, and oftentimes they're found on on mountaintops or very exposed areas. So they're really hardy plants, and they're really good at living in stressful environments. So they're really good at living on green roofs where we can only put a little bit of soil, a little bit of growing media, because if we put a lot, well, the roof would collapse because of the weight. So we can only put a little bit of soil, and it's real hot, and it's real sunny up there. So we need a hardy plant to live. And sedum and succulents are just that plant. However, when we install succulents, sedum, onto a green roof, there's only a limited amount of benefit or ecosystem services that we can get from that sedum. It's the different kinds of sedum, they're diverse, but they're all succulents, and they all grow relatively small. And no matter how much money we spend on a green roof and how many different kinds of species of sedum we put there, the amount of benefits that we're going to get from that green roof are going to kind of top off. However, is there a way that we could increase the ecosystem services that are provided by that roof? And so really, the question is, how can we increase these ecosystem services? And one of the ways that we might be able to do that is to increase the diversity of plants that we use on our green roofs. Here on the left, we see a grass. And I'm going to refer to these grasses in the future as graminoids. A grass is just this kind of grass with blades, whereas a graminoid refers to grasses, sedges, and rushes. They're all kind of closely related to one another, and we're going to refer to them as graminoids. On the right here, we see two different kinds of forb species. Forbs are generally erect-growing plants with a central stem of some kind and leaflets coming off of them. And we have lots of different kinds of forbs that are available. So we think that if we integrate, or research has actually shown, if we integrate graminoids and forbs into our green roofs, into mixed vegetation, we can actually increase the ecosystem services that are provided by that green roof, because greater diversity could actually increase these benefits. And here we see a picture of what one of these beautiful roofs might look like. A meadow with a great degree of diversity, variety of grasses and forbs, and even some succulents down here. However, mixed vegetation generally has very low survivorship, meaning the individual plants that we plant die. And in a variety of different studies, we see that there's 10, 20, 30, and even 0% survivorship of native plant species when they're planted on green roofs and mixed species. So anything that was a graminoid and anything that was a forb tends to die off. So this is a problem. We need to find plant species that are able to survive on green roofs that are not succulents. So what affects survivorship? Well, there's biotic factors that affect plant survivorship. It has to do with species traits, like, for example, the growth form. Different grasses may survive better than forbs, and different characteristics, even within each of those grasses, may affect the individual survivorship. Interaction with other plants might affect survivorship, facilitation and competition, and interaction with other trophic groups like herbivory or microorganisms could affect plant survivorship. There are also a suite of abiotic factors that affect plant survivorship, such as the temperature, the amount of sun, growing medium, and water availability. So the objective of the study that I'm going to talk about is to evaluate the effects of abiotic and biotic factors on survivorship of plant species assemblage. So first I want to talk about what a plant species assemblage is, and where we selected our plant species from. A plant assemblage just refers to a group of species, and we selected species assemblages based on plant communities that have similar abiotic and biotic conditions to that of a green roof. So we found ecosystems where there weren't many trees, where it was very exposed to sun, and the soil was low in nutrient quality, and there was little water availability. These ecosystems, the Hempstead Plains and the Rocky Summit Grasslands, occur around New York City, here in Hempstead Plains in Nassau County, and Rocky Summit Grasslands are up here in the Bear Mountain Harriman State Park area. Hempstead Plains were once a historic grassland, the one prairie that existed east of the Mississippi. It covered 20,000 acres on Long Island, but it's now relegated to one small patch in Nassau County. And so this is a globally rare ecosystem. Similarly, the Rocky Summit Grasslands are not very common because they only occur on mountaintops, and we went to each of these systems and selected common plant species that represented each of these given ecosystems. And we selected 8 different species from each of these ecosystems. And what you'll see is a growth form key down here. So we selected 3 different graminoids from each one of these ecosystems. One nitrogen fixer, which is a plant species that takes nitrogen from the air and makes it available to plants in the soil via a nitrogen fixation process. And we selected a variety of different kinds of forbs. And so what you'll note is that from both Hempstead Plains species assemblage and Rocky Summit Grassland species assemblage, we have 8 different plant species, and we have the same combination of growth forms. So in both we have 3 grasses, 3 grasses and 5 forbs, one of which is a nitrogen fixer and one of which is tall in stature. And so what we did was we took these species assemblages and we planted them on a roof here. And we planted them in these 12 plots that were planted on the roof that were then cut in half. And we put on one half of the plot, we put the Rocky Summit Grasslands, and on the other half, we put the Hempstead Plains. Note that Rocky Summit Grasslands will always be in blue, and Hempstead Plains will always be in this sort of maroon color. And in each one of these plots, we planted 100 individuals randomly planted in each plot. This image here, this sort of technicolored looking quilt, was used as a planting map. And so we actually have a record of where each and every plant is planted in each and every one of these boxes. And we actually put these plots or these boxes at 2 different growing media depths because we think that that's an important factor in determining plant survivorship. Then we planted these plants on 10 different roofs across New York City. So therefore we have a recorded location for 24,000 plants all across New York City. This was all planted in October of 2010. So here's what this looks like. Here is on Staten Island. You can see some of these plots looking very pretty. Here we can see some of these plots in Chelsea. And what I want you guys to note about this is that there's a clear structural difference between the two sides of the plot. On the right side, we can see Rocky Summit grassland that's growing several centimeters shorter than the Hempstead Plains, which is on the left. And we can see that the Hempstead Plains appears to be mostly grasses, where the Rocky Summit grassland appears to be mostly forbs. And so let's see what our data ends up looking like, if it supports that observation or not. And it turns out it does. Of the 16 different plant species we planted, these 6 had greater than 50% survivorship, so greater than 50% survived after 2 years. And when we analyzed these data using a statistical approach called variance component analysis, VCA, what we determined was that species identity explained almost 36% of the variation. What that tells us, what that means is that, for example, Schizachyrium, little blue stem right here, had a survivorship of about 70%, whereas some of our lowest performing species had a survivorship of around 10%. And so what this tells us is that there was a huge range in the survivorship among species. And so that says or suggests that species identity, or the selection of species for a green roof, is critically important towards identifying or towards creating a successful green roof. And a successful green roof is, of course, one that has high plant survivorship, so it's able to provide those ecosystem services. And what you'll see again is that the Hempstead Plains plot species assemblage was dominated by these 3 grasses. Whereas in the Rocky Summit grasslands, we see that forbs were actually some of the most dominant species, mountain mint and bush clover, as well as this tiny little clump growing grass that only grows maybe 7 to 10 centimeters in height, just a couple inches. Okay, and I'm going to skip this one and get to this one, because I think, how am I doing on time, by the way, actually?
You've got about 10 minutes.
About 10 minutes. Okay, great. So I will talk about this one right here. So this image shows, this is the first figure we're looking at here, and this shows what we planted these things in 2010, and then we measured them in 2012. So in 2010, you'll see that the distribution of forbs, graminoids, and end-fixers, end-fixing forbs, is the same between the Hempstead Plains and the Rocky Summit grassland. 2 years after planting, when I measured survivorship of these plant species again, whether or not they were green and still living in 2012 when I went and measured them, what we found was that grasses by far came the dominant growth form in the Hempstead Plains, whereas in Rocky Summit grasslands, forbs and end-fixing forbs became the dominant feature, increasing to over 50% of the composition. So what we see is that even though these 2 species assemblages have the same combination of grasses and forbs when they were initially planted, the composition is changing over time, and different kinds of groups of plant species are becoming dominant. And that will have serious implications for the amount of and type of ecosystem services that are provided by those given species assemblages. Okay, so let's talk a little bit more about that and those differences between these 2 communities, these 2 species assemblages. This image shows, in fact, that we had these initial species assemblages, then we had various survivorship, a couple species kind of fell out, and then we had a couple that became more dominant. As a result of that, and the traits of those individual species, we had different amounts of sward height and plant cover. let's start up with this sward height. Sward height refers to the height that plant vegetation grows to. And we measure it very simply by taking a meter stick and measuring how high the plants grow, okay? And we measured in a variety of different places and take an average. And what we find is that the Rocky Summit grasslands is just in general about 10 or so centimeters shorter in height compared to the Hempstead Plains. Now, what does this tell us? Well, this tells us that the Hempstead Plains may have a greater amount of above ground plant biomass, suggesting that it may capture more carbon from the air than the Hempstead Plains. It also suggests that perhaps the amount of leaf area in the Hempstead Plains is greater than that of the Rocky Summit grasslands. And a greater leaf area would actually potentially have greater cooling potential for our rooftop as well. However, the Rocky Summit grasslands may have greater floral diversity because it's dominated by more forbs that are flowering. So the biodiversity implications, or the amount of different species that we might see on the Rocky Summit grasslands, could potentially be higher than the Hempstead Plains. This figure suggests that there may be trade-offs between the groups or the assemblages of species that we're using for these mixed vegetation green roofs. Now, what you'll also see, and what I think I forgot to mention, was on the x-axis here is plant survivorship. And so again, that is the percentage of plants that survive, and here it's reported as a proportion. So as you have a greater percentage of species surviving, you will see an increase in the height of the community, of the species assemblage. And as you have less species surviving, you have a lower sward height. And that makes perfect sense. That makes perfect sense. Okay, and so on this bottom figure here, we're actually showing plant cover. And what we see here is a similar relationship. We see a similar relationship here where the Hempstead Plains is generally having a higher percentage of cover compared to the Rocky Summit grasslands. However, here we see a significant interaction effect. And we analyze these using linear model, mixed model ANOVAs, which just allows us to evaluate whether there's an interaction effect and take into account random effects. And what you'll see is that the slopes on these lines actually differ. Noticing that they cross right here. This means that there's a significant interaction. And what this tells us is that the amount of gain that we get by having higher survivorship for the Hempstead Plains is less than that of the Rocky Summit grasslands. So we get more bang for our buck with the Rocky Summit grasslands when we plant more individuals or when more individuals are surviving. Okay. And to put this in context, we can estimate that the amount of plant biomass that is above ground in the Hempstead Plains is almost 300 grams per meter square on average. And the Hempstead Plains, the Rocky Summit grasslands is about half that. When we compare that to other ecosystems, we see that it is a similar, it sort of falls between a typical grassland and a typical alpine tundra, and that sort of makes sense because these ecosystems are in fact grasslands that we've installed on building mountaintops, and so it sort of falls in between there. Okay, all right, so why don't I have more to talk about, but I think I'm about out of time, so why don't I take a second and see if anybody has any questions. Does anybody have any questions for me at the moment? I see Angela's writing something. Perhaps not. Okay. So I'm going to just skip ahead a couple slides.
Jason,
then,
Angela had a couple questions.
I'm not, is it coming up in the, I didn't, I did not see that right there. Excuse me. Sorry. How is plant cover measured? Are you, the systems together? Have you or will you test this? So for the first one, plant cover is measured actually just using a visual estimation. So we look at the plot and determine, the same observer determines the amount of plant cover for all these plots. And a number of different studies have shown that if you're measuring these things at fairly small scales, you should be able to estimate them fairly closely. And so I did all of the visual estimates. However, you can do this using different kinds of software as well. So if you wanted to really, really precisely and accurately measure percent cover, you can actually use a free software called ImageJ, and I just wrote it right into there. And you take a picture and you sort of you put it into the computer, and it tells you the percent of cover. So it's super easy to use. And have you or will you test the better plants from each of the ecosystems together? So that's a good question. We have these plots are long-term plots. So we're taking these species assemblages and leaving them over a long period of time, and we're actually looking to see at what happens to them over time. So now, however, we can take these plant species and make recommendations to others to test them further, and for others to take them and specifically measure the traits of the individual plant species to figure out, what precisely are the differences between these different species. So I haven't personally worked any more on these plant species to date yet. Perhaps another question? Good question. And so when green roofs are installed, they're sort of installed as a layer cake. And so I didn't have an image of that, but there is a series of layers that are put down on top of the roof to protect it from water as well as the root systems. And then there's even a drainage system there as well that prevents it. So there's almost at least a minimum of 3 or 4 layers between the soil, the growing media, and the roof surface. Plants that would be potentially more that may provide a greater risk to rooftops are actually things like trees. And trees are generally not grown on roofs that have thin amounts of growing media or soil. Instead, trees are usually used for green roofs that have much deeper soils. And you basically have to design a rooftop specifically to be able to withstand the loads that are associated with using trees or really deep soils. And actually, if you were to pull out the bibliography that you could share, that you would. The video is going to be available. Yeah. And let's see. Yeah, the video is going to be available and the presentation is going to be available, so you could look all of these up. And I could probably provide a bibliography. Yeah, that shouldn't be a problem. We can put that in some of the online resources and make sure that that's available to you guys in the next week or so. So I think that's, and what I did want to say, Angela, was that I have some cool images where if you take some of these grasses. The roots are amazing in plants. And basically they'll hit the ground and then they will just immediately go horizontal. And they'll just kind of look like, I don't know if you've ever looked at sod before, but the way that the roots, they just kind of flatten out on the bottom of these plots and they just kind of extend all the way. So it's quite neat to take a look at. Okay, so I want to just end with one last little piece, skipping a bunch of things, but I want to just end by saying, I want to conclude by saying, humans are ecosystem engineers. We have designed the cities that we currently live in today. And we can now, as we gain a better appreciation and understanding for the way that humans and nature interact and the ecosystems that are provided by our decisions, we can make better informed decisions and build a better future for ourselves by integrating green infrastructure into our urban environments. And so there's lots of people to thank for all the research that I've done. And that's my email address if you would like to ask me any questions or reach out to me. And with that, I'm going to turn it back over to Amanda, who will introduce Paloma.
Awesome. Thank you so much, Jason. That was really informative. I haven't heard that much about your research. So it looks like all the questions have wrapped up for you. So I'm going to go ahead and advance us over to Paloma. There she is. So now I'm going to turn it back over to Paloma Krakower. She's a coordinator of professional development here for us at the Wildlife Conservation Society. Take it away, Paloma.
Hi everyone, it's lovely to be here with you this evening. Hopefully you can all hear me. Can you just give me a quick thumbs up if that is indeed the case? Alright, so Summer, thank you for that. Okay, and Angela, thank you. So this evening how I'm going to connect our talk with Jason's research is really focusing on watersheds. So we are going to be talking a little bit about urban watersheds, but also the greater Hudson River watershed. And can you guys really quickly in the chat box just let me know what a watershed is? So if you have any idea what a watershed is, just let me know in the chat box. See Summer's typing there, so I'm just going to hold off for a minute here. Summer said it's any part of land that is covered by water. So yes, in a sense that a watershed is an area of land that drains into a body of water. It's also known as a drainage basin. So a watershed can have many different streams or rivers or lakes that flow into a larger body of water, and that larger body is usually what gives that watershed its particular name. Jason was talking a lot about ecosystem services before, and if you remember, they're the benefits that people get from nature. So watersheds provide us with our drinking water, and whether it comes from a reservoir network or from ground walls, all of our water comes from watersheds. For example, in New York City, drinking water supply provides about 1.2 billion gallons of high-quality drinking water to about 8 million New Yorkers every day. And not only are they important for water quality, but they also help promote nutrient cycling. They help filter out pollutants, just similar to to green roofs. They also help with carbon storage opportunities because intact natural land cover and soil resources are able to sequester carbon and therefore offset green gas emissions. And there's also economic benefits. So for instance, relying on nature to do its work and its job, we don't necessarily have to spend money on infrastructure or water treatment plants, etc. So it really provides us a great amount of ecosystem services, and it's also really dynamic ecosystems that support a great deal of biodiversity, both plant and animal species. And most importantly, in the context of urban ecology, with the issue of stormwater runoff, so they help basically, let me backtrack there. So urban environments, right, have a lot of paved surfaces, so many concrete and many other surfaces that are not able to take in water like soil would. So stormwater runoff increases the probability that pollutants and debris will enter our watershed networks because there are no natural buffers, so to speak, to prevent this from happening. So really, watersheds are awesome, and they provide us so many, many services. So as we were talking before, the outflow point determines the greater watershed. So for those of us who are in New York City, that might actually only be us presenters. It is sometimes hard to remove ourselves from thinking from the urban jungle to the greater seascapes that surround us as an island. But the Hudson River has a very large presence here in our urban landscape, and therefore, not surprisingly, we are part of the Hudson River watershed. The river itself is about 315 miles, ranging from the Adirondack Mountains all the way to the very bottom of Manhattan. And as the slide says here, the Hudson River watershed is home to about 5 million people and encompasses 5 states, which are New York, Vermont, Massachusetts, Connecticut, and New Jersey. So it is quite a big section here. So what I am going to do in terms of talking about how you can relate it to your classroom, we are going to do basically approach watersheds as if they were a unit. So, Earth Labs, which is a resource from the Science Education Research Center at Charlton College in Minnesota, and their partners at NOAA, or the National Oceanic and Atmospheric Administration, and also the National Association of Geoscience Teachers, and Turk, which is a nonprofit education research and development organization. They all launched this program called Earth Labs. So if you can see my pointer right up here, this is their website, and I'm going to encourage you guys, once this webinar is over, to check them out. It is going to be on their the resource page of this webinar, because they have some great opportunities for you guys. So unfortunately, I was going to try and do a Google Earth software run-through with you guys, but the software is a little too sophisticated to share in real time on this platform. So I am going to share with you some pre-selected images that will hopefully do a sufficient job of painting a general picture of the messages I'm trying to deliver. And for your reference, you must have Google Earth downloaded on your computer in order to do this activity with your students. So keep that in mind when you are thinking about modeling it with your students, that you have good internet connections in your classroom, etc., and that you have the tools. Maybe a smart board would be a great opportunity to utilize this. So the U.S. Geological Survey has created the EDNA Watershed Atlas, and EDNA stands for Elevation Derivatives, for National Application. And that can actually be downloaded directly into Google Earth. And if you are to use Google Earth, you will need to download also the KML version of your watershed. So that was a lot of technical information there, but it's all spelled out for you on this website, on the Earth Labs webpage. So once again, we're going to focus on the Hudson River watershed. Okay. So right here is a very zoomed out image of the Hudson River watershed. Let's see. So I have decided to use a couple of different layers through which we are going to examine the watershed today. The first of which right here is a population index for persons per square meter. And oftentimes when we think of New York, we only think of New York City, or at least people from outside of New York. So this image shows us that much of the Hudson River watershed is not very densely populated until we move to the lower regions of the territory boundary. So for instance, let me get this. So not until we're down here, right, do we see that the population densities start to really increase. Okay. And this is just a more zoomed in version of the same map, so we can get a better picture of New York City down here. Okay. So another feature that you guys can use with Google Earth is also land cover. So I chose to include the 2001 land cover distribution of the watershed. And once again, this is the whole picture here. And I'm going to give you a more zoomed in of New York. So as we can see, as we're getting closer to New York City, right, we have much more urban land cover sections. But a great big part of New York is actually covered in croplands and pastures, as you're going to see there. Okay. So I want to turn this back to you guys, and even though I've posed it as probing questions for your students, right now I'm going to ask you guys the same questions, and feel free to either use your microphone or to type in the chat box. So I'm going to ask that after playing or looking at some of these layers on Google Earth, what sort of connections can be made between population and land cover? And what could this signify for the watershed? And that can be in terms of biodiversity, any sort of connections that you can tell me about. So I see Angela's typing, so I'm going to give her a section. So pollution from agriculture and pollution from urban areas are headed down to the estuary. Yes, 100% correct, Angela. And what do you think that means for the estuary? Not good. Correct. So as Angela pointed out, some of the connections are that urban areas are also very high population areas as well, and some of the least populated areas are forested and or cropland or pastures. So farmland occupies roughly about a quarter of New York State's land area, which in 2012 was estimated to be about 7.2 million acres of land, which is quite a significant amount of our state. So we already know that watersheds are at high risk for pollution. As water travels either over the land surface or through our aquifers, it has the potential to pick up any pollutants that it comes in contact with and deposit them into the watershed or some of the other streams or feeding water bodies. And this is quite dangerous for both human health and the health of other biotic communities. In addition, 153 miles of the 315-mile river is actually a tidal estuary where salt water from the sea and fresh water from the watershed meet. And as some of you might know, and I'm sure Angela hinted at it already, that estuaries provide habitat to thousands of different species, and are often called nurseries of the sea. So estuaries are influenced by ocean tides, but are protected from the full force of ocean waves, winds, and storms, and therefore provide safe spawning areas for many marine species. So if these pollutants from agricultural or urban areas are getting into our watersheds, it has ramifications both for our drinking water quality and also for the health of many of these unique marine species that only spawn in certain areas. Okay, so I am going to now show you, these next few slides are going to be utilizing the stream layer feature of Google Earth. So each image is going to show you the distribution of streams with different values of CMS, or cubic meters per second, that basically is measuring water flow. So it is essentially just separating the streams by size. So the first image here is a stream that is greater than 500 CMS, which is only associated with the lower section of the Hudson River estuary. So it's about 62% of the entire estuary here. So this next image here, with this little purple section, is 250 to 500 meters CMS, which represents the remaining 58 miles tied to the Hudson River estuary, which flows down from Troy, New York, all the way to the bottom of Manhattan. And as you move through the layers and identify smaller and smaller streams, the number and distribution of these streams grow, as you will see in a second. So with each new slide, we're introducing more and more streams of different CMSs. All right, so I'm going to go through those one more time so that you get a better sense. So here is the deepest or the fastest flow rate. And then that's the entire estuary. Until you see all of the different stream layers within the watershed. And as you can see, there are so many smaller streams that eventually all filter into the Hudson River itself. So that's a great way to see the watershed in its entirety there. So I'm also going to show another feature, which is a layering feature on Google Earth, and that is the elevation feature. So I have zoomed in to the Catskill Mountain region, so you can see the difference in topography between mountains and areas of lesser elevation here. So as you can see, these mountains have a little bit more of this yellow color, which are showing you higher elevations through topographical features on Google Earth map. And a very cool feature when you are able to use Google Earth Live is that you can take virtual flying tours of a given area. For our purposes this evening, I have taken a few still images of a tour that I did of Hunter Mountain. I am a little biased. I grew up near Hunter Mountain, so I picked it because it felt like home. So I want you to pay particular attention to the types of streams as they relate to the CMS, or the cubic meters per second, remember, that exist in this tour. So I'm going to show you, and I want you to pay particular attention to the different streams that you're seeing, okay? Oops, sorry about that. So once again, and if it's helpful, feel free to look over at this key so that the colors are represented here, okay? So we're going to take a little bit of a tour again of Hunter Mountain. Okay. Now I have an image of New York City here. And as you can see, the topography from New York City to the Catskill Mountains region is quite different. And so I'm going to pose another question for you guys. Okay, so what are some statements of relationship that you can make when you are examining the elevation and stream layers? When you took the virtual tour, what size streams did you find closest to the mountains and why? And second question is, how would the elevation of New York City affect the watershed in a significant way? What do you guys think? Any thoughts? Oh, okay, Angela's typing away. Okay, let's see. Yeah, I agree. I'm sorry about that. So it's a little hard to see the colors of the streams, but it looks smaller. Faster streams were in the higher parts of the mountains. So, yep, you hit the nail on the head there. So as you were seeing, there were smaller streams. So basically, if we go back to this slide here, right? These streams are either at the 0 to 0.5 CMS, or for instance, we have one here that is at the 0.5 to the 10 CMS. And so basically, when we're in these higher elevations, right, because this particular area is generally very forested in terms of the land cover, a lot of the precipitation gets infiltrated into the soil and goes directly back to the plants. So the runoff that we get is these slower streams that eventually build into the Hudson River, right? And when we think about the elevation here of New York City, we don't really have all of that forest cover, right? So any sort of precipitation that is happening, and let me go back to this image as well. This is the 500 CMS stream image, and it goes right through the tip of Manhattan there. So it's showing us that Manhattan is part of the fastest flow rate. So we're part of the fastest flow rate in New York City, and we don't have the soil or the natural land cover to take in any of this precipitation. So essentially what is happening is stormwater runoff. So because the paved surfaces are limiting the potential for stormwater to be collected, the speed at which debris or pollutants are able to enter the watershed are greatly increased. And that has significant ramifications in terms of the pollution factor there. So I'm now going to hone in on a specific location here in New York City. And although I'm focusing on New York and New York City, you guys can do this for any sort of watershed that is in your home area. That Earth Lab website will have a list of watersheds all throughout the United States, so you can do the same activity with your students in your own local watershed, so it has more relevance for them there. Okay, so I have selected Pier 40 here because it is a hub of environmental organizations that use this pier to do research and different educational programs right off the pier, and it's also located right on the water front. So a really cool feature in Google Earth is the time-lapse feature. You will see it on the bottom of your screen down here. If you click that button, it gives you the opportunity to go back to, in this case, 1978 of that same location all the way up to present day. So you can see the change over time. For our purposes, I have used 4 different time-lapse dates. So this is the first one. This is the edge of that square pier where you saw before. But I want you guys to focus your attention on the surrounding areas over here. So this is an image from December 2001. The next image, once again, remember to focus your attention on these areas over here, is from October 2006. This is from June 2010. And last but not least, this is from October 2014. So I'm going to go through those again so you guys can see it. So this is December 2001, October 2006, June 2010, and October 2014. So what sort of changes do you notice when you are using this time-lapse feature? And when you were paying specific attention to detail in that one section, what did you notice there? And how have urban planners changed the landscape of that specific area? So Angela says some green spaces have been replaced, the concrete, which is exactly right. So urban planners have installed bioswales, as Jason was talking about before, to help prevent or assumedly or lessen the effects of stormwater runoff, similar to the effect that green roofs have. And it's also not bad to look at, right, when you're out enjoying the leisurely activities out on the pier. So ecosystem services not only have to do with biological and also financial benefits, but also the recreational and health benefits that are associated when people have increased access to nature. So it has a dual facet there, right? Okay. So I'm going to briefly show you this graph that is from the Water on the Web website. And as this graph shows us, urban areas have the largest amount of stormwater discharge that can enter our watersheds. And the higher proportion of impervious surfaces causes precipitation to flow into drains, and the rate and speed in which water can travel in urban areas can also increase the effects of erosion on stream banks, and also allows greater debris, both natural and not natural, to enter our water networks. So this next slide here, I have been looking at some of the research on student learning by Dr. Michael J. Brody, who is a professor at Montana State University in their Department of Education, and he specializes in science and environmental education. So he was able to find in his research several important misconceptions of students aged 9 through 16 about their understanding of ecological issues. So he has 5 bulleted examples here, but I wanted to really focus your attention on 3 of them. My apologies, I did not bold one of the 3, which I wanted to talk about. But the first one is anything natural is not pollution. The second one, that biodegradable materials are not pollutants. And the third, that human race is indestructible as a species. So I want you guys to, once again, turn to the chat box or use your microphones and tell me how you would address these misconceptions after learning more about the urban ecosystem, both from Jason's talk and what we have learned so far in Google Earth. Right. Give Angela a chance to respond there. Wait one more second. Okay, let's see. So Angela says, I think showing and discussing the ecosystem services and seeing that when the services are limited or eliminated, that could adversely affect humans to the point that they might not be able to survive as a species. So yeah, that is very profound stuff, right? So a lot of times we don't think of sediments or minerals, right, that are natural parts of the ecosystem. We don't think about the ramifications or the negative impacts that they can have when they are actually deposited into our watersheds. Or a classic example is, you think of like an apple core, right? You throw it on the ground here in the city and you say, hey, it's biodegradable, it's not causing any harm. Except concrete is concrete, and that apple is not going to go anywhere until eventually it has the potential to go into our sewage system and also have negative impacts that way. And slowly but surely, all of these small little acts, right, eventually jeopardize the health of the ecosystem, which ultimately takes care of us as humans, as a species. Let's see what else. So when rain, go to natural paths. So you could talk about the path of rainfall or precipitation, right? And how that might be altered in urban environments and what that really looks like, right? So another way that you guys can address these misconceptions is to actually go out and take this knowledge and apply it. So you can have your students engage in water quality monitoring of the Hudson River or any other watershed in your area that exists in your area. And so these are certainly just an abbreviated list, but these are some of the things that you could test for: dissolved oxygen, pH, turbidity, etc. So as you guys know, fertilizers are rich in nitrogen, especially, and those promote algae growth, and that can choke out the oxygen, which is very important for other species. And it also helps, it doesn't help, it hurts the primary production in aquatic ecosystems as well. And I was talking about sediments before, how they can clog waterways and actually change the chemical composition or profile of a water body. Temperature is also really important in how it relates to aquatic environments, and phosphates and nitrates play a very similar role often with algae growth. And once that algae explodes or takes over, it has that totally negative ripple effect. And urban areas tend to have really high phosphorus levels, more so than other land cover areas, because of this excess stormwater runoff issues. So once again, you can have your students, as an extension, investigate the environmental ramifications of extreme ranges of any of these chemical and physical facets of water. Let's see. So I want to briefly end my presentation here, but before I do that, I want to ask you guys how you would extend this unit further in your classroom. What are some next steps you could take? So once you guys have an opportunity to write down some of your thoughts, I'm going to give you a classic examples of how you could also utilize this more high school related content in a middle school capacity as well. Angela says maybe you could look at the local river system, then do some comparisons to other land use areas. She also has seen satellite images that show sediment in the river outflow that could go along nicely with this. And exactly, so you could look at urban areas versus more agricultural areas. You can look at urban areas versus forested areas, etc., etc. So doing that comparisons is a great way to look at the effects of different watershed ramifications about where people live and population densities versus land cover. And anything to do with satellite images or real-time images is also really helpful for students to realize the actuality of what is actually happening. So you live in a rural area. Yeah, so many times students, specifically in urban areas, right, do not realize that they are actually surrounded by nature, and it's nice for rural students to be able to see the differences as well between where they live and the urban landscape as well. So thank you for contributing those ideas, Angela. Appreciate that. Some other things that you guys could also do is you could have your students use the data that they collected and engage in authentic data analysis and graph creation. And like I said, I know that this unit idea is focused on more high school level, but you could easily take this and apply it to middle school as well. For instance, here in New York City, 6th grade, there is an emphasis on highlighting the diversity and interdependence of life, as well as the flow of energy. So the Google Earth experience might need to be scaffolded more for middle school students with greater content preparation beforehand. However, water quality testing is something that they could do, and it's a perfect opportunity to talk about the flow of energy and the interdependence of life as it relates to both biotic and abiotic factors. You could incorporate food webs and or mirror webs there. And also for 7th graders, earth science is the main science that they study that year, with geology curriculum units, and highlighting the Google Earth activity with a focus on topography as it relates to watersheds could be a great connection, because as we know, topography and geology go hand in hand. For instance, streams owe their early existence to uplift and tilting of stratified rocks. So that's a very nice connection. And last but not least, 8th grade connections can be achieved across this whole unit because of the focus on human interactions with the environment. So the needs and trade-offs are inherent conversations that you can have with your students that could be used and even tied into social studies units. For example, 8th graders could do research on history of how residents of the Hudson River watershed have been making extensive efforts over the past few decades to return the river to a healthy state and make an environmental recovery. So there are many ways for this unit to meet both the needs of middle and high school teachers, and I just really wanted to thank you guys for taking the opportunity to listen to me, and I enjoyed talking to you. Let's see. So Angela has a question about how to use Google Earth effectively. I will say Google Earth is a beast, so I would encourage you to play around with it beforehand yourself, before you incorporate it into your classroom. The great thing about this Earth Lab from the I'm forgetting where it's from right now, I'm sorry, but the Earth Lab website is that they have step-by-step instructions. Thank you. Step-by-step instructions on how to actually download Google Earth, how to get the watershed platform installed, and playing around with the different features. And it also gives you some questions that you can ask and different functions and layers that you can play around with. All right. So at this point, I'm going to turn it back to Amanda, or ask you guys if you have any more questions for myself and or Jason. And if not, have a great night.
Great. Thank you so much, Paloma. And I want to thank everybody here for taking the time to listen to our great presenters. It was such an informative presentation by both Jason and Paloma. Any other questions before we move forward? It looks like Angela may still be typing. All right. So a couple reminders before we let you go. Please remember to log into the Moodle course site. We have some resources available right now. We'll also be uploading more resources throughout the week, and we'll have the recording of today's webinar up there tomorrow as well. Additionally, we had a webinar last night. The beginning presentation by Jason was the same, but the connecting presentation by Paloma was different and geared toward the elementary students. So if you also teach elementary students, feel free to look at that recording and check out Paloma's shared lesson plan there as well. We'd greatly appreciate it if you'd take part in a survey for us. I've posted the link in the chat box. You can go ahead and click on the link there. We will also have this link posted in the email that goes out to you tomorrow, as well as on the course website. This feedback helps us make our programming even better, so it only takes a few minutes. Additionally, you can get a PD certificate that recognizes the effort you put into your professional development this evening. Please email my colleague, Erin Prada. Her email address is on the bottom of this slide to receive your PDF certificate for tonight's webinar. Last but not least, nope, that's got out of order. There we go. Last but not least, take a moment and sign up for the student webcast on October 14th at 11 a.m. if you're interested. Jason will be broadcasting live to your classroom with a modified version of tonight's presentation. It's a wonderful opportunity to incorporate any of the ideas or resources from tonight's webinar into your classroom and give your students access to a real, live, awesome scientist like Jason. I'm going to go ahead and copy and paste that link into the chat box as well if you are interested. This information is also available on the course website if you don't have the opportunity to do this right at this moment. Upcoming webinars in this series will continue our focus on urban ecology, particularly in a seascape. Specifically, we'll look at organisms related to the New York seascape, such as whales, sharks, and the American eel. We'll keep updating our calendar with our speaker topics, but please continue to check back at our website and register at pd.wcs.org. Thank you so much for joining us today, and we hope to see you all in future webinars.